So we got a nice little exercise in visualization last time. In general, I would find part of you probably more flexible for just visualization part that ImageJ is ever going to be. It appears that it depends on your hardware as well. So part of you has worked a little smoother, specifically in the visualization component. That said, ImageJ still has a lot of useful resources in terms of algorithms that you cannot find in a visualizer. Okay, so in that sense, we have to dance between both, and that's how life in general in simulation is. Yes.
Are you recording?
Yes, I am. Thank you. Yeah, I did not. I just started talking, so the recording is probably just went into my stream of consciousness right there. But this is continuation of lesson 7 on quantification of surfaces, and we're gonna do finish surfaces today and also mention curvatures. So let's get going. I want to make a quick comment. So your homework, next homework, is probably going to be assigned on Monday. That is going to do surfaces, and I'm actually include some 3D printing. So you will create the surface. You will probably be tasked to create anything you'd like. Pick your surface, porous medium surface that you're excited about. You can grab it from your data. You can grab it from Digital Rocks portal data. I don't care. Something that is nice, little printable. And I will bring samples on Monday of what I expect from previous class, what I expect you to kind of zoom into. Now, the level of details will determine the size of your STL, stereolithography file, the two in. And I want you to test Maker Studio. Now, we have a 3D printer downstairs, but Daryl is typically very busy printing whatever is needed, printing parts, also 3D printing parts for experiments in this department. So instead of flooding him with 20 printing requests, I'm going to let you flood engineering center. There's so-called Maker Studio, Maker Space Studio, where you can go and 3D print. Okay, so I'm going to investigate a little, but you can probably Google it just as I can.
Do we have to be an engineering student to use that?
I wouldn't think so.
I think you have to.
You have to be? All right. Well, you will find a kind person to submit your job for you. Okay? And if not, I will be that kind person. So there should not be a problem. So find a friend. This is why we socialize here 3 times a week. So you can find an engineering student friend. But it is kind of exciting to see a 3-dimensional printout. It's going to be a bit of an optimization because there might be limits on the file size on what you can print. Okay? Level of detail is typically going to be the smallest, so you will have to tell it, hey, here is a structure, and print me something on the side. What's its side size? So let's say 10 centimeters or whatever, right? So you have to tell it the scale. It doesn't know necessarily the scale from the file because that's not the information that travels with the file. Okay? Now, you have to be careful that the smallest feature that it can actually print is about 0.3 millimeters. So as 3D printing is very exciting in porous media, we know that we do depend on scale for limiting transport phenomena, so getting something down to the scale you'd like it to be, okay, for your experiment, so you can 3D print your rock before you do experiment. That's still not there. So I'm going to actually share a paper that goes into that. Part of the problem in increasing this detail is that if you have smaller resolution, your pore space would collapse during printing. And in order for it not to collapse, they figure out fillers. But this being 3D complex geometry, then you can't get those fillers out. We know that everything about residual phases in a porous medium, right? It's not surprising that you cannot necessarily get those fillers out. And then you have these fillers sitting in the pore space, which is not what you want either. And there's actually a paper that goes into weeds of those for geosciences purposes and says, yeah, you can get the smaller resolution, but you're going to have all of these residuals in your pore space, and you might not want that, right? So there's a bit of a dance there between the resolution, getting the resolution you want. Also, the printing procedure itself, say you want a pore that is on the order of 1 mm. So when your resolution is 0.3 millimeters, okay, then it's plus minus that. So let's say that you wanted a 600 micron pore, you're going to get anywhere between 500 and 700, right? So, and that's not good enough for our purposes. Also, there is actually apparently a lot of microporosity created near the surface in the process. So if you do MICP of that pore, you're going to get the pore that is 600-ish micron, and you also got some smaller pores on the side that are essentially microporosity of the material during the printing. So there's a little bit of, we're not there yet in terms of printing ourselves, our models. In micro models, that would be really exciting if you could 3D print, because then all of the fabrication problems in micro models where you have to carefully attach and seal the top surface to your micro model after etching would go away. So I'm presumably within 5 to 10 years we're actually going to be there, and you will go on some online thing, print yourself a micro model or some sort of rock structure, and deliver it by Amazon or by a drone to the top of this department. So there's a lot of excitement. I'm gonna, part of the homework, we'll be sharing some 3D printing. There's some cool TED Talks, so you can just amuse yourself just to get your imagination. There's nothing wrong with letting your imagination go, because that's how innovation happens. But there is a lot of, specifically in industries, such as in mechanical engineering, where parts are designed and there are actually surfaces that are flat. If you're designing anything, if you're designing a machine, that machine has cylinders, annuli, parallel plates, and, am I missing anything? Spheres, okay? Beautiful, pretty, easy to design, easy to print too, okay? So in that sense, you can, whatever it is that you're designing, you can actually 3D print an actual surface of it before you, and you can also, presumably, down the line, do so with parts. So there's actually, with some advanced materials, you can actually 3D print. Let's say that I don't have an arm, God forbid, but I could actually get an extension, 3D printed biomedical device that would be customized to me, okay? And that is a great advancement for those who need it. So in that sense, like, let your imagination go. It's actually a really cool technology. And we're gonna look at a little bit of how can we use it, if nothing, for education, okay? All right, so just a quick recap in terms of smooth and binarized data and how does it affect surfaces, okay? So I might have 3 scenarios. I might have detailed analytical information that I use to create a surface, and I use it. So this is an example. Let's say that I have a sphere packing. All of my spheres are analytically described, okay? I can actually create a sort of a field of distances to my sphere surfaces and just find an isosurface 0. And when I either produce a surface or want to print it to an area, I'm going to actually get a really nice surface that kind of renders something like this. Okay, so this is my smooth rendering of spheres. So that's great. In our imaging process, we typically don't have that smooth surface and analytical description, okay? So more likely than not, I might actually have some sort of segmented data, or I had tomographic data that in itself looks smooth, okay? But I might need to use advanced segmentation in order to remove certain issues with noise. And therefore, the segmented data is the one that I trust the most. And if I create a surface, I'm going to have the staircase effect because I have kind of 0-1 situation, and I cannot necessarily create a smooth surface. Any smoothing that I introduce is actually artificial. So beware of that. It looks better, but it's actually artificial. Okay? So that's just a warning there that you might have some staircase effect, or if they look smoothed, that's fine for the looks part, but you have actually introduced the smoothing yourself. Now, even if you have data that is analytical, there is still, if I digitize it, so I have to put it on grid, and that's what I do whether I'm doing numerical simulation for it or whatever it is, you might still have some little, like it might actually near the sphere contact, so this is where I'm supposed to have a point contact. I cannot resolve a point, a mathematical point, however much I try. So you might have some funny looking triangles there around that contact area. That's all fine. Okay? It's not a big deal. It's plus minus 1 voxel around that contact. So your surfaces might have a little bit of, when you're trying to precisely resolve because of the numerical issues, you might get a little bit of finite resolution effects. So just a warning out there. Yes?
So in the last image, the one that is binarized,
Mm-hmm.
we see this stair effect. This is kind of a roughness of the surface. Does this roughness affect the physical simulations?
It might, depending on your physical simulation. So the methods, and we're going to actually get to that a little when we get to the methods themselves. The method, the lattice-Boltzmann modeling, okay, is actually working with an image like that. So even if you have a smooth surface, it doesn't really matter.
Okay.
But yes, you might actually, because if it's sort of an artificially looking, you know that your flow, if you have it finally resolved next to that, is going to start recirculating.
Yeah.
Right? So you're going to have little eddies, even though your Reynolds number is really small. Okay, so that happens, okay? And that's something that we now most of the time for petrophysical purposes, we are really interested in permeability. Permeability in itself doesn't really care what happens next to surfaces all that much, but mostly what's happening next to in the major pathways through the middle of the pore space. So middle of the pore space carries most of the flow, typically 90% of it, and the side effects are, inertial effects in these corners are not a huge deal. So that's, all right. So good visualization always provides insight. This is actually, let's actually see whether this movie still works. Oh, okay. If my mouse now moves, it does, okay. So this is 3 spheres, okay. You can see a little bit of resolution. This is just a visualization issue. You can't see the mouse? Okay, I'm gonna, you can see a little bit of, this is just a visualization from the scene. And this is actually an interface between 2 fluids, wetting and non-wetting. This is a throat, what we call a throat, in between 3 spheres. Okay? And I'm displacing a wetting fluid, okay? And I know I have a curved interface. Now, if I was in a tube, it would be part of a spherical cap. Okay? Here it's not, it's a meniscus. It's possibly part of the spherical cap, this part, but then it has a concave part going in between these spheres. Okay? And we're going to talk about these curvatures a little. So I'm pushing through, and then there is a moment, which is the critical curvature of this throat, after which, when I increase my capillary pressure, okay, I have nothing to hold me anymore. So I kind of have to push through, and I drain my entire throat completely. Okay. So if we were doing MICP experiment in petrophysics, that's basically what you're pushing through these stages in multiple throats across your porous medium, but it's throats that are holding you, right? And basically, once you push through, what you're left with is now your non-wetting fluid is here in the middle. We don't see it. You're only seeing the interface between the 2 fluids. That's the visualization part, where you have to really visualize only the interface and not the entire fluid. And what's left is these pendular rings around sphere contact. So if I had like some water in between my fingers, I would see a pendular ring, right? Those of you with water bottles can try. So this is essentially my water here next to contact 2 spheres. So this would be my irreducible water in soil, right? Or any kind of granular medium. And typically this water is not going to move, it might evaporate, okay? But it's not necessarily, I can't displace it. Now, simulation, this is three-dimensional surfaces, three-dimensional space. How this portion happens from here to here, it's kind of difficult to see just from images. And if I had a larger simulation, it would be even more difficult to see. And I'm going to show you when we get to we're going to talk about this simulation later when it's a little more advanced. This is the simulation part. Okay. So, but good visualization or creating a movie does make a whole lot of difference. Okay, let's see if QuickTime will play it. It's not showing. You don't see it?
The mouse was on the original. I think it's doing like a dual monitor.
Good point. I see it here. Swap displays? No? Let me do the mirror displays. Move. There we go. Mirror displays.
Oh, you're good now.
Oh, maybe I can just play it from here. There we go. Okay. So now you're looking at the triangulated surface of the sphere, so I can see through it. Otherwise it's going to block my view. And you're going to see the red interface, which is interface between non-wetting and wetting fluid coming through. Okay. So these are just different stages put together. Blue was that critical stage. And then I push through, and my interface essentially aligns with the spheres here. But here I have some residual water, and the non-wetting fluid or oil is in the middle. This, everyone, is my claim to fame in 2006. All right. There's a level set method that was new, and in the time, nobody so far kind of showed this three-dimensional push-through in a generalized geometry like this. Okay. Now it's a good day. Everybody does lattice Boltzmann simulation that does the similar thing. Back then, not so much. So I left a room in Denmark speechless when I showed this. All right, let's go. Come on. So now I need to switch the type of the display. Come on. So I see, swap displays. There we go. No. It's not swapping. Okay. And I can't do mouse, can I? I'm just gonna do this. Oh well. So second part, this is actually part of my thesis. And you will see this on Digital Rocks board also. This is a Berea sample. This is a see-through geometry of my sandstone. So it's an interface of a sandstone, just like the one we actually visualized last time around. And what you're seeing is residual non-wetting, could be oil or gas, blobs in the pore space. So technically these are now disconnected and you can't get through them. Part of my PhD was actually analyzing an entire experiment where the middle section was imaged in X-ray scanner. It was one of the first of such images back in the day. And there was this displacement going on, so there was like image was taken at the residual water saturation and the drainage, then residual oil saturation at the end of imbibition. Then there was some gel placed in there, and then the drainage and inhibition was repeated, and the imaging was repeated as well. And we looked at what are these residual blobs doing and how are they hanging, how are they different before and after gel placement, and they were very much different. But one thing that I did is like, hey, let me look at the largest, this is just a portion of an image. So this is a simulation that was simulation in this size of an image. So it's highly unlikely because of the boundary conditions that I'm going to have a large blob sitting in there at the residual state. However, if I was simulating over a larger medium, that could have happened. The snap-up could have happened. And in the real example, it did. So this is my largest residual water blob at the water residual. It's quite large. And this is the largest residual oil blob. And this is equivalent of the exercise you're doing for homework. You're just doing it in a couple of pores. And you can actually already see by the shape that this thing is hanging out in the middle of the pore space, and this thing is hanging out on the surfaces because it's the bedding fluid. And part of that, you erode and look at the connectivity exercise. It's like, well, can I see that in terms of numbers, Euler characteristic, connectivity, and so forth? So can I characterize it? With numbers as opposed to visual. But this is, again, this is their physical location is completely disjoint. Where the part of the pore space where my largest residual water hangs out is completely disjoint from where my largest residual oil blob likes to hang out. And I'd like to think, I didn't analyze that, but my explanation was most likely in this portion of the geometry, the pores were generally smaller. And in this portion of the geometry, the pores were generally larger. Okay? So my sort of the disconnected larger blob would like to sit in that portion of the pore space as opposed to this, because we know that the bedding fluid likes sort of smaller pores, microporosity, and so forth. Okay? So that's something, and that's type of the insight that you can get with good visualization of what's happening, specifically three-dimensional stuff and the heterogeneity of the pore space. So this is what I call good visualization does provide insight and can lead to your intuition about what the crux of the problem could be in whatever it is that you're trying to tackle. So while visualization in itself kind of sounds a little trivial, where you're just visualizing whatever it is, whatever the simulation you did or whatever experiment you did, it's not trivial. There's an important component is to visualize and to communicate whatever it is that you found to others. Putting together good three-dimensional visualization as well as movies is kind of an effective part to communicate the main result of whatever research you've done. So think about that when you do that. All right. So here's some practical examples of interfacial area measurements. So we're just going to comment on quantification and how do I verify if I got good areas. So if you want to come up with test configuration, just like in our comment on segmentation, you come up with something that you know. What we know is typically spheres, okay, and we have analytical formulas we can test against. So get something. This was that same sphere pack that we looked at during the segmentation lectures. So either capillary tubes or spheres of different diameters are good test examples. And note that for very nice, precise spheres, you have to spend quite a bit of money. It's not the regular stuff you get for cheap in order to get like all of them nearly the same size. Okay? Now, this is actually a test. You can look at this paper from 2010. So this was basically looking at the two-phase segmentation of this precision sphere pack, and then all kinds of various methods of finding area. Okay, and there's percent error. Here's that infamous voxel count that we said is a big no-no. Well, this is how big of a no-no is it? Okay. You're going to have 45% off, even in this very nice precision bead pack. Okay? Second part is we didn't actually do two-point correlation, but it still persists as a common way where like you do a two-point correlation function and where it intersects zero, y is equal to 0, no, x is equal to 0 axis, or r is equal to 0 axis. That's where your supposedly your area is, and there's theoretical result for that, but not so much verification computationally, because that's the second runner-up in being really off. Okay? So I wouldn't go with either voxel count or two-point correlation. Everything else is doable. MC refers to marching cubes. So these are variants of marching cubes. Okay? So you're okay even if you do the basic binary marching cubes. Those are okay areas that you can limit in these sphere packs that are very well. Okay. Now what if I have multiple phases? Here's the problem that I run into. Let's say that I have, this is my solid, two-dimensional solid, and I'm marking solid voxel centers, but this is an actual pixel, right? That all of these are solid pixels. And this is, let's say, oil and water at 90 degrees, some sort of 90-degree contact angle situation. Yeah? If I wanted to create a surface, so I have a problem here because of the digitization errors of how do I create surfaces between all of them and actually a triple contact line between all three of these spaces. So technically I know that it should be, this should be my contact point between all three phases, right? And if I have things correct, this would be my interface of one of them, interface of the other, interface of the solid, right? And they would all intersect at this point. Yes? If I was placing surfaces to separate these voxels, technically I should kind of include this corner of this voxel.
It's not clear because we cannot.
Oh, you don't know what am I pointing to? And you'd say I'm tall. Apparently I'm not tall enough. All right. Here, this is basically the line that should go all the way in between these two phases, right? Except that if I do marching cubes, and that's the only thing I can do to computationally find these interfaces, I can't do 3 at a time. I can do 1 and everything else at a time. So if I do just solid and everything else, then my interface is this line, right? If I do just, what did I call this? Water, oil, one of the phases, then my interface is yellow plus green plus this cyan color. So it has this little thing here that we get when we are creating triangulated surfaces. This was just in 2D. And the same thing, mirror image of it, yellow plus red plus that magenta color, would be the interface of this phase. So if now I'm looking to intersect them, okay, intersection, which would be my wetting, non-wetting area, let's say, or oil-water area here, would just be this yellow thing. And this contact point, I wanted a contact point between all three, triple contact point, is actually this triangle, whatever it is. Right? And in 3D, that object gets bulkier and more complicated. And here I am, I'm a petroleum engineer, I'd like my contact angles, thank you very much, in a complicated pore space, right? So identifying it is not so trivial. Because you have this, so you have to find a way to somehow extrapolate this yellow all the way to the solid phase, right? And get all of this as the area. So that's the digitization issue. So in terms of just estimating the area, okay, just estimating the area, what's typically done is, one thing that I do, so we do have confidence in computing interface area between one phase and everything else, but if I have multiple phases and I want this interfacial area between pairs of multiple phases, I run into trouble. So since we have confidence in computing interface between one, if I just wanted a formula what I do is the following. So what if I compute interface area just between solid and everything else? I will get these two, right? This perimeter in 2D of this line and this line, okay? And you can't see what am I talking about. This line and this line, right? So that's my solid area. Great. Now let's do just vetting area. Just vetting area is this. Yes? Non-vetting area is this. Yes? So if I add vetting and non-vetting, okay, or here it's air and water. So if I add air and water in this image together, I'm going to repeat solid area twice. Yes? And, or rather, I'm going to get solid area plus this non-vetting here. Area between air and water, right? Twice. That one will get repeated twice because I'm going to repeat it from this side and from this side. Yes? So basically, my area between air and water is 1/2 of summing these two together minus the solid area. So I go and for every phase that I'm interested in, I compute area between that phase and everything else. I might have multiple phases. Okay. And then for these pairwise areas, again, if I add air area, the air is the other side, and then water area together, these portions will be counted twice, and the rest will be solid. So this portion that I'm interested in is 1/2 of the sum minus that solid area. Done. Got this? So now I can verify that works well. And again, if you do this in a capillary tube, you know what pressure is and all that, so you can actually compute what that area should be because it's a spherical cap. Okay? Or you could just fit a sphere and measure it that way. So if you do, again, do not do voxel counting, do not do point correlation, but this marching cubes is doing actually really well. Okay. So just to get the area out, it's fine. Visualization is still an issue and might need to intersect and extrapolate. And I actually did that. I'm going to show you those videos when we get to the simulation part. Okay. Now let's actually look at the interfacial area measurements from the actual experiments and what are the type of numbers that you get. So this capillary pressure functional relationship, we know and use it a lot for drainage and describing drainage and imbibition in petrophysics, right? And we know that I'm going to have what's called hysteresis between drainage and imbibition. Okay? And part of it is then, and that's kind of an important part, is actually creation of areas in your system. So it's as you're moving through during drainage, you're pushing to non-wetting phase and you're creating new interfacial area between that phase and everything else. Then you're going back. Okay? Some of that work is stored in the areas and you're not going to get all of it back. So the efficiency of the process is not necessarily 100%. And part of that work is now stored in these areas. So measuring areas thermodynamically, it's a relevant thermodynamically process, especially if I wanted to somehow remove that hysteresis and have a better relationship. It's not functional relationship just between capillary pressure and saturation, but it possibly involves multiple variables, and area is one of them. Okay? Now, I would like to measure area. Area measurement is tricky experimentally. I have BET method, but there are some assumptions built in how molecules that you let into your sample line up on that area. So that's based on gas absorption. So there is an assumption of the singular molecular layer, which might or might not be there. Okay. So there are models assumed. Image analysis has resolution issues. We know everything about that. Okay? So if you didn't image a certain part of the area, well, you're not going to measure it either. So, but nevertheless, this imaging, so maybe I can actually help. I don't trust either of the methods, so maybe I could go and have two different measurements and figure out, because ultimately we want to describe these processes that are happening near the areas that are important for our physics. Now, in terms of theory, I'm not going to bore you much with the slide, but basically this is the efficiency. If you're into thermodynamics, then Morrow's paper from 1970 or Hassanizadeh and Gray from 1993 go into the details. But they're basically looking at my capillary pressure. I can look at it as a change in Helmholtz free energy of the system, energy available to do work, for both phases. So there's this difference here. And also, whatever change I have in interfacial areas in the system, because that's where some of the energy, I need energy to create area as well as to destroy. And basically, you can also evaluate the thermodynamic work done is the area under capillary pressure curve, by the way. So you can actually look at this efficiency of this process. So the whole point of this slide is that there's an entire line of theoretical work that is trying to add this area into the description of capillary pressure and saturation in order to remove hysteresis. And with the advancement in both imaging and computational methods, suddenly, 20 years later, we are actually able to try to verify this, okay, computationally. Let's compute the areas. Let's see if I can find a functional relationship between all three terms, capillary pressure, area, and saturation. And I know that I'm gonna do well, or at least that I have semblance of doing well, if I do this for drainage, I do this for imbibition, and I get the same functional relationship. Therefore, I remove the hysteresis, and I'm just looking at different projection of it in the phase spaces. So these are some measurements from experiments. This is from work of Dorothy Wildenschild. So you will see typically that during the drainage, this is drainage, for instance.
Which one?
So look at the drainage, one of the curves. Drainage, of course, I start with relatively small area when I don't have both phases in, or not a lot of them. I have a maximum somewhere in between when I have both phases splitting space half and half, so to speak. And then as I reduce to a residual, then one of the phases, there's so little of it that I can't have a lot of area either. So my area will always have this shape. Yes? This is just interfacial area between non-venting and venting. Great. So this is some measurements and how they look like. I still have a little bit of solid and empty is drainage and imbibition. So I still have slightly, so I will have sort of hysteresis between the two if I just look at the interfacial area and saturation. However, as this is more measurement, and measurement from computation. So I can do simulations, or I can actually image. These are actual imaged experiments of displacement. Okay? So both ways I can try to compute these areas. And let's see how these surfaces, this attempt to actually put together a surface. So if I look at the area versus saturation and capillary pressure, actually, to quite a good match, they're off about 5%, I will get similar surface from drainage points and imbibition points. However, when I still see discrepancy when I just plot capillary pressure versus saturation, which is what we normally measure and normally see. Because these are two different projections of this same surface. Yes? So there is some evidence, at least in these measurements, that this theory might hold water. No pun intended. Yeah? Might hold oil. No, just kidding. Okay. So there's, again, right now, in terms of both ability to image experiment, ability to do simulation, we have the ability to verify some theoretical assumptions out there that are just done on pen and paper. Okay? So you should think about it in your work, no matter, this is one example, but no matter what it is, there is, again, ability to verify theories, because computational advancement as well as experimental imaging are kind of at the right moment, at least from for the conventional materials. For unconventional, well, work is in progress, okay? Because it's a multi-scale problem. So again, this error between this surface area pairs is up to 10%, which is not a big deal. When I get up to 10% difference, I'm not going to write home that it's a big news. I mean, it's a pretty good match, yeah? At least in these areas. Okay. Now, of course, with this is some area measurements in simulation. So whenever I get simulation, I actually have to, if I want to measure area, I have to proceed just like if I imaged, same thing. Okay, so I have images, even though they're actually simulation results. And how I actually produce this area estimates is the same. So this is basically, we're going to comment on lattice bolts and simulation, but the simulation can actually be pretty good. This is actually imaged experiment, and this is simulation with different lattice Boltzmann methods, and it's a pretty good match. Okay.
Is it the same pore space?
Yes, the same, similar pore space. The problem, of course, is that you're gonna, as we know, you're working with the segmented image for simulation. You segmented image from here, and that has some inherent error. Okay, and of course, you see only as much resolution as you discretize the space. You don't see all of these fluids see in the experiment. So that's always there. So this is a pretty good match the way, especially this one. So this is segmented image, and these are the two fluid simulations compared to that. So I see some differences. And a little bit of a small difference in resolution or something can throw off the result. Typically, look at it statistically in terms of multiple realizations or similar fluid connectivity behavior, like the connectivity that you're just analyzing now for your homework. So don't go into one-to-one. One-to-one does not exist in terms of boundary conditions applied and so forth. Applying the same boundary conditions in experiment versus simulation is never there. Okay? The sizes of the volumes will mismatch, and it's never going to be completely the same. However, that shouldn't stop you from trying, because in trying to match the two, you will learn. And actually having a difference is more insightful than having everything matching. Okay? So we can actually find. And then, of course, just let me finish this thought. With any kind of discretization of the space, depending how good is your resolution, your simulation will follow. Okay? And that might or might not match the experiment completely, because you're starting to miss out on details as your resolution decreases. Okay? All right. We're going to do curvatures on Monday then.
Is the homework still due tonight?
You can finish it over the weekend. I'm not going to assign another one till Monday. So.
This is what I'm supposed to expect.
Just, or maybe I should just say tomorrow night, so you don't spend the entire weekend. How's that?
This is what I should expect from the behavior of the other characteristics. This is for the pore space.
Not a number, no. What is that?
Oh no, this is part of the. This is for the.
How many steps do you have? Oh, that's a lot. 5 steps.
Yeah.
I see.
The thing is that I get different components for each step.
Ah, okay. So take the largest component. I think I call it.
Yeah, but this is a earlier characteristic.
What's the best way to separate
So this is
to like
you guys got the same similar behavior for biofilm. Start here and start to go up.
Okay. So when you usually have a lot of very negative oil characteristics, because you have essentially one connected component, and all other stuff
Biofilm,
that
is
makes
it just the
it
biofilm? Because it needs to be binary, right? So you need to call the pore space something else.
because you get more.
Yeah, and this is it's supposed to push it down because you're reloading them.
Yeah, that should be.
So this will be a film and the red is the rest of the corpus, so it's attached to the grains.
Okay.
And that's
That's inseparable because that's if I want to say, well, where is it? You can
Yeah.
kind of average the distance if you like.
okay. All right. I just wanted to
Mhm.
check. Thank you.
I have a question about instruction.
Instruction.